All right, so thanks everyone for coming to our Tuesday seminar. It's my pleasure to introduce my friend and co-author and collaborator, Dr. Sarah Kaiser, streaming all the way from West Coast, Australia, or no, West Coast, USA, where it is what time? Late?
Just after 5.
Oh, okay. Yeah, we're not in the, yeah, we're not in the skip ahead, jump back thing yet. Right.
I'm taking my long black with Mr. Black.
Right. Okay, all right. Well, take it away, Sarah. I guess you give us a really kind of hands-on introduction to Q#, and I think everyone will enjoy it.
Yeah, well, thank you so much for inviting me, Chris. And I'm really excited to speak with everybody today and kind of share what I have learned about kind of quantum development more generally. And in this case, show you kind of how, show you a little bit about Q#, which is Microsoft's quantum open source quantum development platform, and how I've actually used it in research. So let's just get started. I should also note, obligatory funding note, all of the work you see here is sponsored by the Unitary Fund, which is a open source quantum programming micro grant project. You can check them out at unitary.fund. But anyway, Chris introduced me, but to add a little bit more to that, I do a lot of different stuff right now. I think I, on LinkedIn, identify myself as a quantum technologist, but I do a lot of streaming on Twitch, where I do live quantum development and programming for quantum computers. I write a lot of books, including some with Chris. And my pupper usually shows up on my streams too, which I will do my best to make sure that he doesn't interrupt here. But most importantly for this audience, I'm also a researcher. So I did my PhD at the University of Waterloo doing experimental quantum optics stuff. I've done some nanodiamond and V-center stuff in Sydney, in fact, at Macquarie University. And now I kind of have shifted into more industry and software roles, which has been a really interesting change and really opened up some really interesting sorts of projects that I don't think I ever really would have gotten a chance to work on before. So today, I'd really like to give you a tour of Q#. So just kind of show you what it is. And then show you a case study of how we used Q# to actually do some research on qRAM, or memory for quantum computers. And then to kind of synthesize that, I want to share some open source tools and resources that you can use to leverage either Q# or any other quantum development platform, and just in general help make your own research more open and reproducible. So let's just get started. What has been really exciting over the last couple of years in quantum computing is that there's been a huge explosion of software tools, right? I'm sure like many people here have used many of these different options. There's a great list on the Quantum Open Source Foundation here that's kind of just scrolling, but there's a lot of choices, right? So sometimes like when we sat down, I was working with my collaborators who, Olivia Di Matteo, who is an expert in qRAM, and we were trying to sort through and figure out like what platform here even makes sense for our project. So what we needed so we just kind of tried to identify from a research standpoint what we were looking for. We wanted to implement algorithms. Because basically our goal with this case study, as we'll look at in a minute, is to basically take a bunch of different papers that had proposals for quantum memories and implement them, and try to do that at the highest level possible. And just because, we didn't want to necessarily embed, say, specificities of the target hardware in with our description of the algorithms. And we wanted to make sure that this was not only a project to get a research solution, but to enable further research and collaboration. So we wanted to make sure we kind of had a plan for how we're going to package and make our work easy to share and collaborate. And we wanted to work with a community where we were all included. So here's my first, and I guess only ask the audience question, which is, what do you know about Q#?
It's hard to search for on Google.
Yes, that is true. generally because the hash is ignored, you basically just get QAnon stuff. So a pro tip for that is if you do Q# and you write out the word sharp, that can help. The programming language from Google called Go has a similar problem, because if you just search Go, that doesn't generally mean the programming language, so they have Golang. But yeah, has anybody else even heard anything about Q#? Maybe you haven't heard about it and are just, yeah.
I think because it's been around longer, people are probably familiar with like Qiskit, for example. So can you introduce Q# by like comparing it to something that people might be more familiar with?
Oh, fair. Yeah, and I can, so let's just go ahead then here. So Q# is Microsoft's quantum programming language. I think Q# has been around longer than Qiskit, if I'm correct. But it is based off a platform called Liquid. But the idea is it's an open source language and that is domain specific for quantum computing. So it is a new language from the ground up. It's not C#. It's yes, branding and naming things is a hard problem for Microsoft, I think, but it is an entirely new language that is designed for quantum computers. If you've ever done high performance computing, think of like GPUs often have languages like CUDA that is designed specifically for that hardware. Because quantum computers are pretty like similar to, you can think of them like hardware accelerators for particular problems. This is kind of like a model that is similar to the HPC area. So Q# is the language. There's also the quantum development kit, which is basically all of the, just like a SDK or software development kit. You get that. It comes with like compilers for the language, runtime, sometimes editors, stuff like that to help you use the actual language. So that's basically what the quantum development kit is. It has simulators and different tools to help you actually write your quantum programs. And it's designed to be integrated based on this kind of hardware accelerator model that we were just talking about. It's designed to be integrated with a number of different languages and platforms like Python and .NET. So you would have your host program, or just like in this figure, if you were to write some Q#, basically what it would look like is you'd write your Q# program here on the left. It consists of operations and functions that you write. Maybe you include some libraries to kind of like help you out. The libraries are kind of just like packages in Python. They're just off the shelf. You grab this one. And together those are your Q# program. That then can be run by a host program. So that could be something like Python, it could be C#, it could be, as you'll see here, a Jupyter notebook, or it could actually even be run directly from the command line. So actually, in some sense, a host program isn't even necessary. But the idea is that then this Q# program, which is not, you're not writing it for a specific target hardware or target machine. Q# basically separates those two ideas. So that you can write a program once and then run it on a number of different target machines. So that includes, so the quantum development kit comes with things like a simulator, so a full quantum state simulator, a resource estimator, and the idea is with Azure Quantum, which coming soon is about all I know. It's in private preview right now, but basically that's where you'll have the same kind of online cloud accessible quantum hardware like you have with IBM and Qiskit right now. So the idea is that your program doesn't have to change for any of these different target machines that you want to run on. So let's sit down. What do I actually write what do I do if I want to write a Q# program? As we saw kind of in the previous figure, there's basically two things you're going to write. You're going to write functions and you're going to write operations. Functions are basically very similar to the mathematical sense of what a function means, domain, range, whatever. They're basically deterministic, like classical mathematical operations like sine, log, maybe. I see somebody raise their hand. I don't know in Zoom how to acknowledge that.
Okay, I have a question in fact.
Mm-hmm.
So QSharp, the philosophy is to write it on any, I mean, it can run basically anywhere. If you, for a PC, that seems okay. But if that's the case, does it mean that QSharp can run any publicly utilized quantum computers like IBM or Rigetti or anything?
That's a great question. So not officially, but so the QSharp community has a project that's basically QSharp integrations, where you can make a target machine, basically compile your QSharp program to like OpenQASM, and then pretty much any other platform can consume OpenQASM. So that kind of has some challenges in that what you can express with OpenQASM is a subset of what you can do with QSharp. So in general, that translation, you are losing stuff just because OpenQASM doesn't really express classical logic as well. Like generally it's like for programs that are purely quantum. But yeah, so there is definitely ways to take programs and things you write on QSharp and run them on different platforms via OpenQASM. Does that make sense?
Yes, that is, but that means like you have to develop different versions of QSharp for different computers.
No. I mean,
because it's similar to like Java. When Java initially started, they said you can run it anywhere. But the thing is, like for the Java for a PC and the Java for a Solaris were entirely two different JDKs. So that's the reason I was asking, like the QSharp for an IBM quantum computer versus the QSharp for a Microsoft quantum computer might be having different versions. So that's to accommodate same kind of functions and all.
Yeah, I mean, I think at a base level, because Microsoft and IBM are competing right now, they're not going to natively necessarily make it easy for both of their platforms to work on each other's hardware. Like, and Azure Quantum, as I mentioned before, is effectively the competing service to the online cloud hardware with multiple different vendors. Like, I believe IonQ is one of the vendors, Honeywell is one of the vendors. So there'll be lots of different hardware and you don't have to write your program multiple times. Like the QSharp is the same. What actually takes care of translating it to the different endpoints is what changes. And you as the user don't have to see that. So let me get back to here so I don't run out of time. Anyway, so you write functions and you write operations. Operations technically cover everything else, but in general, if you're working with qubits, I kind of mentally try to think about this as like operations are where I'm working with qubits. Functions is kind of where I'm messing around with classical data. So let's do a hello world here. You always got to do that with a new language. So I'm just going to run these cells. So I'm actually running this Jupyter notebook has QSharp running, a QSharp kernel running in the background. So this is one of the ways you can actually use QSharp in the notebook like this. So I've defined a function here that takes an argument name and has a return type of unit. So anywhere you see these colons, that's basically the typing for QSharp. So QSharp is a typed language. And as noted here, everything in QSharp is tuple in and tuple out. So you're always going to have basically an input tuple and an output tuple. So if I actually run this function, and here the notebook kind of magic command here is called simulate. So what it's doing is taking this function and running it on the quantum simulator that comes with the quantum development kit. Obviously, since this is just basically a print statement, it's not doing anything interesting. But you can see here I can pass it the argument, and here's the tuple out that I get. It's a unit. It's unit because it still has to pass me the tuple even if it's empty. But that's a good thing to remember when debugging, or I find helpful when debugging. So obviously we probably want to do do quantum stuff with Q#. So what would a hello quantum world look like for this? I tend to think of like a qRNG as kind of like a hello quantum, or like a quantum hello world sort of example. So I'm going to start by opening actually one of the libraries here. So kind of just like you would use import statements in Python, I'm going to open the Microsoft.quantum.measurement namespace, and that adds, allows me to use mresetz kind of with this shorthand name like this, and I'll define the operation. You can see here, actually we'll look at it in a sec, so let me just run it. And wow, super amazing. Oh, okay, there we go. It's like, is it not random? No, so obviously every time we measure this, what's actually happening here? So to use qubits, we use a statement here called using. And basically you can kind of think of that as like, so you have using, there's arguments here for that basically say how many qubits you want. So this is, you're basically asking the target machine, hey, I want some qubits for this next scope. Please, I need, in this case, we're just asking for 1, but you can easily make it, you know, however many you want by indicating it with arrays there, or with a bracket in the number. And then you see these curly braces here, and that basically defines the scope over which you can borrow, or you can use those qubits. By default, using here will give you qubits in the 0 state. And your promise to the runtime is basically when you give it back, they will also be in the 0 state. So, you know, for our qRNG here, all we're doing is applying a Hadamard to the qubit, and then returning, basically measuring the qubit in the Z basis. So that's, and also resetting it. So that just means if we measure it in 0, we don't do anything, but if we measured it in 1, we'll apply the X to actually get it back to 0. And as you can see here from the colon, the return type of this is actually a result. So if you look when we ran this, the result type has two possible values, 0 and 1. Cool. So what else can we do? There are things called functors in Q#, which their names might give away what they do, adjoint and controlled. And basically what they allow you to do is very easily generate new operations from operations that you have without you having to like write out what the adjoint or what the controlled version of that operation is. So in this case, what I'm doing here is I'm defining a new operation called apply multi-controlled C0. So it takes an argument of a control register and a target qubit, and it does an X operation, so that's a poly X on the target, but I actually also have this argument now because I put the controlled functor out top in front. That means now I can basically, to whatever I'm applying this control to, I basically add an extra argument at the beginning. That's my control register. And then Q# will apply, you know, this operation controlled on this register. So let me run that. Obviously, this is just another way to basically define a C0. There's also a built-in C0 if you want. So here, I'm going to, I want to actually, so we've defined this operation now. To actually simulate it though, I need to actually allocate some registers and get some qubits to use it with, right? So I'm gonna open one other library here called diagnostics, because we're gonna actually look at what the simulator knows about our qubits and stuff as we're going through this. So here's our using statement again. I'm going to make a control register of 2 qubits and a single target qubit. And I'm going to basically put the controls in superposition. So here I'm applying Hadamards to each of our control qubits. So you can see some kind of very functional like sort of flavor to some of the stuff in Q#. I feel like from what I understand and have used in other programming languages, I'm normally a Python user. I feel like there's a lot of Python influence and some like functional Haskell sort of influence. But really every design decision basically comes back to, does this make sense for a programming language that describes quantum systems? Like that's the whole point of making a new language, right? So everything has to kind of be synergistic with that. So great, we put our controls in superposition. Then we use the operation that we just defined, apply multi-controlled C0. And then we're going to look at actually the state of all of our entire machine, in fact. And then here at the end, we're actually just resetting. We're not doing anything with the qubits, but we have to reset them to make sure that the compiler is happy with us. So I will run this now. And what you can see here is that a dump machine built-in kind of function here gives us, especially in Jupyter Notebooks, a really nice printout of kind of what the state of our qubits are in. So if you recall, basically, so we've got three qubits here. The first two are control and the last one's our target. So because all the controls are in superposition, I think this is the state I'd expect here. So we can see it's 0, 0, 0, 0, 1, 0, 1, 0, 0. So all of those are basically all of the bits, possible bit strings of the first two, as well as the last one here. So, and the only time the last bit is 1 is when the first two are 1. I was trying to think of an example that was like not trivial enough that, but also not too complicated to think through in my head. And this is where I settled on. If anyone has better ideas, I would love to hear. But anyway, so this is just one example of a place or a method in which we can actually run our Q# programs. So as I kind of mentioned before, you can run them from the command line. You can run them from Python or .NET. And you can run them in Jupyter Notebooks here. I'm actually using a Q# kernel. So like these cells are native Q#. Or you can actually have a Python notebook, which is what we do in our qRAM library, where we can basically do all the pre-processing on the data that we're going to put in the memories in Python first, and then do all the plotting in Python afterwards. And it's a really pretty easy experience, like transferring the data back and forth. So, and in terms of like target machines, so we saw in the kind of diagram before of kind of what running a Q# program looks like, there's lots of different options for the target machines. You can use LS Magic here to basically show you all the target machines end up looking like these magic commands, at least in Jupyter Notebook. If you're running it in like from the command line or from another program, they're basically just arguments to the run or simulate command. But here you can see there's lots of different things you can do. We've mostly been using simulate. And you can also see here a whole bunch that are for the Azure Quantum service as it comes online. So you can actually, even directly from the notebooks, you'll be able to submit jobs to the web, to the hardware in the cloud. But some of the other things you can do with different target machines is you can do tracing. So say you have a program, and actually we had this come up in qRAM quite a lot, where we wrote the code for how we think, the algorithm as described in the paper was, and we had some circuit diagrams from the paper, and then we had the circuit diagrams that we had tried to synthesize and simplify, and we wanted to check to see if that made sense with the code that we actually implemented. So one way we checked that was actually by using this trace, which runs the simulation of the operation or the program more generally, and then draws the circuit for it. So that's actually a reasonably new feature. Another really, really helpful target machine that you can run your program against is the resource estimator. So it's really easy to basically take a program that you have, maybe you're interested in how it scales, and obviously, we all know that it takes exponential classical resources to simulate quantum resources. So at least on my machine, even though it's a fancy glowy gaming machine, I can only simulate about 32, 33 qubits on it. Fully simulate, fully general. I can estimate because this estimation algorithm doesn't actually run the circuit, it just counts the resources needed to. So there I can estimate the resources for much, much larger circuits. And that's actually something that we leveraged very heavily for the qRAM project. So one other really helpful thing, especially that we learned from doing the qRAM project, was integrating unit testing, which is kind of a fairly common software dev practice, into actually our research testing. So primarily to check to make sure that what we have actually implemented for the code matched the paper results. So, sometimes papers have like the plots of the resource scaling, or maybe they'll have specific examples worked through. We were able to use data like that from the papers and effectively write unit tests for our implementations to make sure that they worked. So things that you can leverage in Q# that are helpful for that are, there's functions like fact, which is basically something that, in this case here, it's checking that the number of qubits that you've entered is, greater than 0, because it wouldn't make sense to allocate a register with 0 or fewer qubits. And the other thing we're doing here is actually like, so all that this test here is doing is effectively allocating a register and making sure that it was all allocated in the 0 state. So each qubit is in the 0 state. And so, yeah, that's basically what we're using that handy dandy apply to each. We have the assert qubit operation here, which basically says I would expect whatever qubit I pass here into this argument to be in the 0 state if I measure it. And here implicitly it's in the Z, measure in the Z basis. There are generalized ones that you can pick which basis you want to measure in. But here you can see a good example of partial application. So I have this, effectively this one argument operation here that I'm going to apply to each qubit in the register. So very sort of kind of functional feel. So yeah, I can simulate that. Ideally, nothing comes out of that and just all the tests pass and nothing happens. One of the things that I thought was really, really interesting was there's one more sort of kind of category of testing helpers that Q# has that was really helpful when we were trying to do basically optimizations. So the idea here is, so the operation is called assert operations equal to reference. And there's lots of different variants here, like that you can specify. You can just check out docs@microsoft.com to look at some of them. But the basic idea is that it uses the Choi-Jamlikowski isomorphism to basically check to make sure that two operations do exactly the same thing, like for all inputs. And so, if we have an operation that we've written and we have another one that we think we've optimized in terms of resources, we want to make sure that those are in fact still exactly the same operation. And so we use this actually a lot to make sure that every time we kind of implemented a new optimization of one of the qRAMs, that it actually was in fact identical to the previous. So here, I'm going to show this by, I have an operation here that applies a C0.
Sarah.
So, yeah.
That seems like it would be incredibly, like that would scale incredibly badly. So in terms of actually, yeah.
Yeah, so basically what it takes is it will need, for however many qubits your operation takes, it will take double, because basically what it's going to do is it's going to prepare a maximally entangled state. And I think it's like on one qubit, or on one half of it, apply one operation and then apply the adjoint of the other, and then make sure that that entangled state is still exactly the same. Because if those two operations were actually identical, doing one and then doing the adjoint of the other should effectively be the identity.
Oh, okay. So you're saying that you lose at most a factor of, you can basically do this for up to half as many qubits as you can simulate normally.
Yeah, that's right.
Oh, that's not so bad.
It's not too bad. And depending on, so other things you can potentially leverage, like for, at least for us for a qRAM, there's also a Toffoli simulator. So that's basically if all of your gates can effectively or efficiently be simulated by like classical Boolean logic, then you can do much more and use this for much larger states. But yeah, you're right. But it's, as far as I understand, just a factor of 2 overhead.
But
So,
I assume this also only then works with the exact simulation and not with the estimation backend?
That's a good question. I'm not sure I've ever, so you can run unit tests against the estimation backend, but I think then what you're comparing, like the results you're comparing, are usually the actual resource counts.
Right, okay.
So I should probably look into do some more of that. Mostly we were just checking to make sure our actual operations made sense.
All right, thanks.
Yeah. So like for the example here that I wanted to show here, I'm just applying a regular C naught to 2 qubits. And then there's a circuit identity that's pretty common of if you basically want to flip the control and target of a C naught, if you apply C naughts, or if you apply H's on each side on both qubits, that effectively flips the entire C naught. So here, that's basically what we've implemented, or what I put here for the second operation. And you can see another kind of neat construction that Q# has, which is called within applies. So if you've ever looked at quantum algorithms and stuff, you'll probably be pretty familiar with this pattern of like, you do some sort of state prep, then you have the actual kind of meat of your algorithm, and then you need to unprepare what you did at the beginning for to make sure everything's reversible. So this within apply pattern kind of is an example of how Q# is kind of really designed for quantum algorithm stuff, because here I can put what my preparation is, and Q# will take care of doing whatever is in this within block. So anything within these curlies, it will take care of doing the reverse and adjoint and everything to make sure it's all cleaned up nicely afterwards. So I don't have to remember to adjoint everything or implement adjoints myself. I can just say, all right, this is my preparation step. Here's the middle bit, and then please take care of the rest for me, which works well for me. So yeah, and we can, let me just run this, and then so we can run check that this works. Since we got it works, the assert, if the assert passes, it doesn't do anything. So this is identical to how like Python does asserts, stuff like that. Ideally, nothing happens here. I also wanted to show one other cool thing. So we looked at the trace, kind of the trace backend before, which is simulate, but also draw what you were simulating. So I can basically, obviously this first level of depth here doesn't really tell me much. Great, it's a box on all of the qubits. I don't find that super helpful, but I can kind of like slowly zoom in and see like, all right, here, here's the prepare, and I can keep kind of zooming in to see, exactly what is happening for each, at each kind of zoom level, if you will. So yeah, that can be a helpful diagnostic tool to make sure like if something is passing when you don't think it should be. But yeah, so that's a neat thing you can do with the tracer. So having kind of looked through a lot of different tools actually, and kind of deciding on Q# as being the right one for our research, our plan was basically to use functions and operations to implement the qRAMs, use the libraries, functors, and other features to basically reduce how much code we have to write, which ideally reduces the number of errors we have to make. We wanted to add some testing to make sure that our implementations match the paper descriptions, and profit, but primarily by publishing, because we're all academics here. There is no profit in publishing. So let's now talk about specifically an example here, as I've alluded to a number of times, of using Q# in actual research. And I realize I had a lot of colons in this title, so it's a case study of Q# driven research, the qRAM library, the musical. Sadly, there are no musical numbers for this talk. So what is kind of the problem we're trying to solve here? Quantum applications might need memory. Basically, memory can be a good way to transfer classical data to quantum systems. In particular, we see this a lot in like quantum machine learning algorithms, where there's just kind of this, we assume we have a qRAM and here's the rest of our algorithm. So that kind of, at least to me, when I was chatting with my collaborators on this, was a problem that kind of spoke to me, because I was like, oh, people, we just assume we have this. Let's actually try to implement that. And so like, you can basically think of a qRAM or a quantum memory as an oracle, a pretty common kind of model that we have in quantum computing. And when you query this oracle, you have a register that you usually give it as the address that you want to query. And the readout can take a number of different forms. You can read out the data at that address as a phase, like in Grover's algorithm. You can read out the bit value as like literally a qubit register, like an element distinctness, or in the element distinctness algorithm. Or you can actually read out the data as amplitude, as a complex valued vector of amplitudes. So that's basically like what you'd see. That vector then would be like the weights for your QML application. So it's not, in general, the problem is it's not clear if we can do this efficiently at all, let alone with fault tolerant kind of overhead added. Like it looks real bad, frankly. And basically what that means is any speedups we see in applications that use qRAMs, basically they're not usually counting the costs for qRAM in their costs. And so basically once you add those in, it's a wash, or possibly strictly worse than doing it classically. So yeah, there's lots of different approaches to how to do this, and a lot of them kind of optimize for different things, whether it's like extremely small number of qubit devices or devices that really don't like T-gates, so you want to minimize T-gates. One of my collaborators here, Olivia, actually gave a seminar for this series a few weeks, in August 7th. So definitely my goal here is not to deep dive on all the different implementations for qRAM, but really just to kind of motivate what problem we were trying to solve. So please go check out her talk here. I will put this link in the chat in case you're interested, but it's basically on the QSI YouTube channel. But she gave a great talk on the scaling and kind of issues around qRAM more generally. So for us, what was, if it looks so bleak, what was the path forward, or what were we even trying to do? We wanted to figure out whether qRAM will ever work. And basically we need a way to evaluate proposals. That's pretty much where a lot of us are at for quantum computing more generally. We've got to do benchmarking. And we really need to compare a lot of different papers, but most of them don't provide any implementations. They're, especially for qRAM, are just descriptions of algorithms. So, it doesn't even in some sense make sense that there would be included code. So, but we needed a way and a platform that we could actually implement all of them and compare them. And, like for any sort of resource estimation project, you want to make sure that your assumptions are clear and made uniformly, and that other people are able to reproduce your results. Because you should always, as the pupper here is helping, measure like 6 times cut once, at least when I'm doing maker projects. Yeah, so yeah, we need a way to implement those algorithms, count the resources, and do it in a reproducible way. It looks like one of my slides did not. Boop. Turn into a slide. All right. So yeah, basically here's the repo that basically contains our library. So this is all open MIT licensed. You can go check it out, and it's on NuGet.org, so you can include it in your projects already. But the basic layout of our repo here, and for the code more generally, is basically we have docs, samples, the actual source, and tests. And then we basically have samples for each of the different kinds of qRAMs and qROMs that we've actually implemented. Here's kind of an example of what it at least looks like it in my editor, which is wholly purple and pink themed. But basically, you know, I can edit my tech here, I can write my Q# code here, I can compile it and do it all in one place. So I included, and again, Olivia kind of goes over this in more detail, but we currently have the bucket brigade, both bit and phase query models implemented. And we also have like a naive qRAM and then a optimized select swap qRAM, which basically gives you a way to trade off between number of qubits and basically circuit depth. So it's a pretty cute little algorithm. So since this is a Q# notebook, let's just use it right here. So I'm going to actually load our qRAM library right in line here. So this is pulling the NuGet package just from like a, you know, kind of like PyPy hosts Python packages. You know, a lot of languages have, you know, effectively package repositories, and NuGet is what Q# uses. I'm going to load a butt ton of libraries. There's tons of stuff we're using and leveraging here to, again, kind of reduce the amount of code that we write, aka also to reduce the amount of errors we can make. Here's some examples of some of the stuff that we've written in the library. So we can write our own types actually to describe the qRAM and qRAM oracles themselves. So that's technically one other top level thing that you can define in Q#. You've got your functions, you got your operations, and then if you want, you can also define new types. And new types are basically tuples of other types. So you can see here, we've got our tuple, and here I'm basically describing the type signature for what a phase query would look like, what a bit query would look like, what a write would look like, and some metadata about our qRAM, so that once I've kind of created this qRAM, I can just quickly figure out like how many address bits it takes, just so I don't have to remember and pass that around separately. And we also have implemented a bunch of different, so these are functions because it's just classical data, to basically generate and effectively fuzz our implementations with a bunch of different memory contents. So here I'm just basically hard coding some sample memory for our qRAM to use. So here's basically what it looks like to use it. I have an operation, so I'm going to be working with qubits. Here, this operation takes actually a qRAM as an argument and what address we want to query. We're going to get some qubits here because we're using the using statement. And I'm allocating two registers, a address register and a target register. And you can see here I'm using some of that metadata or named components of our type here to just make sure that I'm getting addresses sufficiently large. I can use so I'm using library functions here to basically say I want to apply a poly operation from a bit string. So anywhere, if I have this bit string that matches my register, wherever there's a 1 in that bit string, I would like to apply this poly, please. Please and thank you. So that's basically what we're doing here. Then this is what it looks like to actually read from the memory. So we have our memory, we have the named item read, and then here I'm passing the address register and the target register. Then we reset the address register because we're done with it, and then we measure the target register. So that's, you know, this is not necessarily representative of like a good use case for qRAM, because you wouldn't take classical data, create a qRAM or qRAM, and then immediately measure it. The idea is that you would use it then as a part of another algorithm. And we have some samples in the repo for like Grover's algorithm. You can replace some of the oracles in Grover's algorithm with qRAMs effectively. So those are kind of more real. Chewy, shh, please come here. Here. My apologies.
Not a qRAM fan?
No, not a food delivery fan. There you go. He is trained from my streams because he hangs out with me. I've got a separate webcam right here. So he will very often just stand basically where he is right now, just waiting for treats. And chat can give him treats whenever they want, or rather ask me to do so. So yeah, that's basically, so if I were to write like a program that uses that operation, because that operation actually took a qRAM, so somewhere I have to actually create that. Here's the operation that would do that. I have it creating some just sample data here. I'm creating the memory with a call to basically our qRAM constructor, and then I basically return the results of that operation that we just saw. So I included here the hard-coded data that's in there at the moment. So ideally, if I simulate and query address 2, I should get 5. That's good news. Good news, everyone. Query 4, I get 2. Again, not like the most earth-shattering sort of result here, but I'm just trying to demonstrate what it looks like to kind of use the contents of our library to implement a program. And without changing anything about my code, I can just immediately look at what the resources it would take to actually implement this. So I can see it'll take, I think it's 7 qubits here. T-depth is 70, and then this is counting like raw totals of each different gate here. And I can actually even define more metrics if there's specific, maybe there's a specific combination of gates that is hard to do in my hardware, and that's what I want to actually count as, you know, being the cost. I can define whatever I like with that with the trace simulator, which is kind of like the generalization of this resource estimator. So yeah. That's pretty much the contents of the library. We have a bunch of tests, as I noted before, that basically we have ones that run on small enough number of qubits that we can actually run on the full simulator. And we also have some that basically just check the resource counts on larger instances. And we also have a lot of docs that basically help other people figure out how to use our work. And also help kind of, in this case, understand what the research problem or question that we're trying to solve here is. So yeah, what's next for our library basically is, so the project finishes the end of this month, I guess. But basically we're working on docs at this point. So we implemented everything we had in scope for this original kind of grant proposal. We're hoping to implement more in the future, but basically we're just kind of working on pulling everything together and writing a research paper to kind of show this process and document it so other folks might find it useful. And so we have basically since we've been doing all this development in the open, all of our like grant deadlines and stuff are all just public as milestones on this repo that you can check out, which is a reasonable segue to the last part 3, because I can count, of how you can start your own Q# projects, which is AKA best practice open source development for research. So yeah, in case you haven't come across the term before, open source software is basically software that can be freely accessed, used, changed, or shared by anyone. Importantly, they usually come with a license that describes you know, any sort of restrictions on commercial or non-commercial use or attribution. But then there's also open source communities, which are basically everything about software projects, but the code. So like the licenses, processes, funding, everything else. So something I'm really passionate about is trying to figure out how we can learn from open source software best practices to make our research better. And there are tons and tons of resources that are out there that basically document, you know, what good surveys of what best practice are for open source software development. I've got a couple of the links here. You can definitely grab these afterwards from the slides online, which there should be a link in the chat for those as well. But like, what does open source research look like? In general, that means having all of the source code and data included when you publish, especially if you're doing experiments, making sure you include the raw data. things that can help you with that is automation. And that's basically kind of where, you know, we can really lean on open source software and the open source software communities to help make our research better. It means citing and donating to open source projects that you use in your research. Like Python is an open source project that has their own basically funding sources or funding bodies that that are nonprofits that you can donate to that make sure people who are doing the development on Python, you know, get paid and stuff like that. Using free and open source tools and platforms to make it easy for other people to use your work. I know sometimes it can't be avoided, like if you're doing, you know, super fancy particle simulations or stuff like that. Sometimes it's, you know, really expensive software you have to use. But having come from the experimental side, like there are lots of tools like LabVIEW and stuff that sometimes are great, but there's often open source alternatives that may make sense depending on where you're at, if you're starting a new project or taking over or have equipment that's not been maintained and has no drivers. So yeah, like, you know, here, everything we're doing, not only the code is available, but any tool you need to use the code is also free and openly available for all platforms. So Q# actually runs on all operating systems, Linux, Mac, and Windows. So yeah, you can use the development kit anywhere. So yeah, I think one of the things that we need to do is find or create these open source software communities in quantum computing. So there are some really good options already that are kind of growing up right now. There's the Quantum Open Source Foundation, which I have the scrolling GIF from earlier. I help run a couple called Q# Community and Wicca. There's the Unitary Fund, which actually funds this project. Yeah, so there's lots of different options, but to just kind of highlight a little bit what this looks like, these open source communities look like for research. So Q# Community is a user group for supporting open source quantum development and research. We want to empower everyone to get involved in quantum development, which includes things like making sure everyone feels safe and welcome, understand how people communicate, and making sure we set up tools that work well for them, and making sure we can support members of all skill levels. So everything from, you know, somebody who is maybe a front-end software dev who wants to get into quantum to some of the folks here who are professors in quantum computing. You know, we want to make sure that we can help support anyone along that spectrum. So I'd encourage you to check out qsharp.community. That's our website. We have some blog posts from our different members with the projects that they're working on. qRAM was a is a Q# community project, which basically means, you know, as projects evolve, we all can help continue maintaining them. And you can see some of so I mentioned earlier the Q# integrations, that's a Q# community project. I also recently wrote at Chris Ferrie's trolling on Twitter, a CHP simulator. So that's basically a target machine for Q# that allows you to run error correcting code, simulate things on error correcting codes. So with all of these open source tools, what does that look like for an actual like day-to-day doing research sort of workflow? So for us, for the qRAM team, it basically meant we did have like a standing time because we were distributed. We had kind of a standing time each day if we wanted to check in with everybody. We had Slack channels for discussions. I'm sure many different universities have like either Slack or Google Hangouts, like some sort of messaging application. We were using tons of different operating systems. So I think each of the devs working on this worked on a different operating system. So we all used basically Visual Studio Code, which is an open source text editor to do all our development in. And basically when we wanted to get together and work on something, I actually would start streaming on Twitch and would invite my other team members to the exact editors. It's like Google Docs, but for our code is the best way to describe it. So you can see this is a GIF of kind of the thing here, but it's called Visual Studio Code Live Share. So I can basically host the program that we're developing or the application we're developing and everyone else can kind of edit and follow along while we're streaming and talking with folks in public. So that was pretty fun. And as a part of this, we also ended up contributing some other tools that we developed as a part of qRAMs. So things like project templates and contribution guides. Those can be pretty useful for your own research projects as well. Basic build automation and testing framework. Use DevOps to make your life simpler. And tools like actually what's hosting this talk right now, my binder and remote development environments. Those really help address the, well, it worked well on my machine sort of problem. So containerization is definitely your friend. So if you want to actually give this a go and try using Q# for your research, I would encourage you to check out, obviously, the docs for Q#. One of the books that I've written recently is actually Learn Quantum Computing with Python and Q#. Frankly, most of the folks here probably don't need the learn quantum computing parts, but the where we start getting into Q#, I think would be a good place if you want to see basically like a step-by-step through the full language. I do a lot of live development on Twitch. What is 10 a.m.? It might be a bad time for Australia. It's 10 a.m. Pacific. I don't know what time that is in Australia. But then I also, my co-author on the book has some repo templates basically for Q# projects already set up. So basically, if you want to start a new research project, you can just clone this. It's got the template set up for your LaTeX. It's got templates set up for all the code and stuff like that, all the build automation ready to go. So yeah, that's pretty much the contents of my talk. I am almost exactly on time. But yeah, basically Q# is a high-level open source language for writing quantum algorithms. So it's focused at the algorithm level in a portable and reproducible way. We've implemented a number of proposals for qRAMs in a Q# library and are working on resource estimations. And the open source community in general is a really great resource for reproducible research. And I would encourage you, as a maintainer for Q#, if you are interested in working on Q# projects for research, come check out Q# community. We now are starting also community calls. So once a week, we'll basically just have kind of a coffee time where people can chat about what projects they're working on. And it's been a pretty good way for people to find also collaborators who might be able to help out or be interested in working on different projects. So yeah, I think that's what I got. Are there any questions? Oh, I hear very faint clapping.
Yeah, it's a sad state, isn't it? These virtual.
I wish, you can mute and unmute and you can raise your hand. Like, I wish there was like also a clap or a face. I missed that from real life talks. Oh, nice. Thanks, Marco.
There is a clap, but sadly, what they need is like an audio clap.
Ah, yeah. Like if you hit that, that should be like an audio cue as well. Nice. Thanks, everybody.
Was there any questions for Sarah? I have a couple. So while people unmute themselves, I'll ask, do you have a sense of like the size of some of these open source communities?
Yeah. So I mean, I know for sure numbers obviously about my own or ones that I help maintain. So Q# community is about 150 people. Wicca is about around the same. I am on the Slacks for a number of different ones as well. And I think things average usually somewhere between order hundreds sorts of thing.
Mm-hmm.
I haven't recently checked counts on things like for Qiskit and whatnot. Obviously, so there is definitely difference in strategies and stuff, and I think like even right now there's the Qiskit coursework and stuff that's been going on, so I think that's been driving some really some good interested, especially like younger students to quantum development, which I think is awesome.
Right.
And
yeah,
sorry, I wanted to comment on that one. What would be the ratio of sort of we're trying to target the classical software development community. What fraction is that community versus people who are already in quantum?
So at least for the communities I manage, it's almost entirely that. I have actually very few people who are in research who are participating in the community. So often what I've been doing lately is some of these classical dev community folks find interesting papers on archive and they're like, oh cool, I really would like to learn more about this, but I can't understand the paper. Sarah, can you translate it? And so like one of the things, and one of the reasons why I was really excited to give this talk is, I want to, as someone who has been a researcher, I want to try and help connect people from, the research community and the classical software dev community, because I think there's a lot of skills that, can synergize here between different individuals to actually make really cool projects. So like, even for example, on qRAM, I helped, Olivia was kind of the traditional algorithms expert. I was the kind of Q# person. And then we actually had someone who was a 30-year classical DevOps person who helped us do all the testing and set up automation and stuff like that. And it was a really fun way to kind of work on quantum research because it was a, new perspectives and stuff that at least I had not experienced, in more traditional research settings previously. And I think that's kind of one of the really interesting situations or impetuses that we have right now with quantum computing is we're at that kind of synthesis point where we want to pull all that stuff together to make this usable.
And do you feel as though you're retaining people, or they sort of flash in the pan, come and do something for a couple of days and then bugger off?
Honestly, there are always going to be some proportion of the flash in the pan people. They usually come after, they join after larger events and then never come back. But of the about 150, I'd say probably a third or more are people who are there pretty regularly and checking messages and stuff. Something we used to, this has been a challenge that I've been trying to address, more generally with, pandemic and distributed nature of the group. So there's a neat plugin for Slack that's called Donut that basically pairs you, it makes small groups that kind of introduces you every 2 weeks, I guess. And so I think that's really, I see the statistic reports for that, and we usually have 50% or more people participating in that. So they're coming back and they're, talking to each other, learning what each other does, seeing that there are other people in the community that, maybe have similar backgrounds to them, but who are interested in quantum or are meeting people who have entirely different backgrounds. And so, yeah, like trying to drive that organic community growth, I think is an interesting challenge, but I feel like it's working, albeit slowly here, but, I, even with like the people who come regularly to my Twitch streams, like I have probably 20 or 30 people who will show up most times and, come laugh and yell at me when I forget semicolons and whatnot, which, yeah, like it's fun.
So how often do you, or like, in the classical devs people, are many of those people interested in kind of getting involved in specific sort of research projects that people are working on, or are they mainly interested in the sort of the more general community participation?
Honestly, they're generally interested in specific projects. I even just recently I had someone who was a regular on my stream, and they had seen an article about what was it? It was a different classical subtheory, not CHP, but it was something else. And they were like, I really want to figure out how to implement this. Like, this seems, really interesting, but, didn't have kind of the, like, even to just read the research paper describing this proposal, the simulator proposal, like, kind of was difficult. And so kind of something I'm trying to put together for the future that I think would be really interesting is like trying to, put together a list of kind of going to talk to both research groups and these folks that are, industry folks that are interested in kind of helping, like trying to like set up some sort of, it's not exactly mentorship, but I guess they're collaborations. Because, you know, what I've experienced now working in classical software dev and working on research projects with classical software devs involved is you get a really different result. And I think in general, a better result, because, you know, things that to me as a grad student or even as a postdoc that seemed wholly out of scope, they can just walk up and be like, oh yeah, I can set up automation for that and we can have it running and tested, you know, by tomorrow. And you're like, what? So yeah, like I've been actually, because I've had a number of these requests from community folks that like, they're interested in X, I've been also trying to find researchers who are working on those and connect them. But that's kind of an ad hoc process that is not super efficient for anyone's time. So I'll also point out QSOF has a mentorship program. So like, especially, this is more geared for students, but basically a bunch of quantum people have kind of put together projects that they want to mentor somebody to do, to develop in an open source fashion. And then there's a bunch of applicants. I think the applications close on the 12th. But yeah, like that's something that QSOF has been doing. And so far, I think they've had one round and it seems like it was pretty successful, because the idea is basically, you know, these are research questions or problems usually that, you know, people have. Software devs can come in, whether they're student level or they're actually like 30-year veteran software devs. They can kind of work together and actually figure out an actual solution to that develops novel research results. So
I think I saw there was a couple high school students even in the last round that produced some research. Yeah.
Yeah, no, it's really interesting. So I'll be mentoring in this next round. And I think it'll be interesting to see, I put out a whole bunch of like different project ideas, but I'm really interested to see like kind of a cross section of what the applicants look like for that in terms of their background. And yeah, I'm really excited to see what projects. Honestly, one of the projects I put forward was to improve the CHP simulator and get it to include kind of like so right now it's very strictly, if it's not supported in that framework, you can't simulate it, but I want to add in approximations as well. So
best tweet ever.
You are very good at was it nerd sniping? So
Sarah, I wanted to just ask like one last thing for the people here, and then I guess everyone on YouTube who's listening and watching. if they're going to first get lunch and then do one thing, like what's the one, I think maybe you mentioned like to go to the Q# community page, but like what's the first step? Is that what they should do?
Honestly, that's a good question. I would say, honestly, open the slides for this talk. This is, you can, here, let me screen share one more time and I'll show you what you can do. Oh, am I still sharing? Okay, there we go. So if it'll open with slides, but basically this is still a Jupyter notebook that you can actually run Q# code in. And so, you know, if I just add a new, I mean, anywhere here, I add a new cell, this is, try running some of the Q# samples here. Try writing your own. Take like, implement teleportation, you know, and you can use the docs to kind of help and guide. Like there are some samples there, so you can copy and paste and try running that. But what I like about this is it's an entirely in your browser experience. You don't have to install anything. You don't have to, you know, you just have to have a web browser and you can actually start playing around with this. So yeah, I would say open the slides and try running some of the samples, try changing things, you know, see if it works. Like I do software development, I call it experimentally, which means I usually write out what I think should happen first. And when it doesn't run, go back and check the docs. So I'd rather build it first and then read later, which is probably not the best route more generally, but I like, I like experimenting. So
And,
go
and
forth and experiment.
And for those that want to, you know, they're stuck at home in lockdown, and want to be involved in these community aspects, they should check out the Slack channels, or?
Absolutely. So slack.qsharp.community will take you to our Slack group. That's usually where our discussions happen. If there's what I'd love to learn from this group is if there's any like research challenges that you're having, whether it's, you know, simulation issues, or you've got something but it just is not super optimized, or you've got something and you want to run it on lots of different frameworks. Like something I'm actually working on right now is trying to make a simulator backend that is easy to use a wide variety of C++ implemented simulators. So there's so many different like optimized classical simulators that we have, and you know, something people like to do is benchmark those, right? But it is often hard to get fair comparisons of those. So like open source simulation or open system simulation is something that I'm actually working on at the moment as a simulator. It's our qTrill project. But yeah, just join the Slack, and I'd love to hear from folks if there's any research things you're interested in, and you know, that can help kind of, I think, introduce yourself. There's an introductions channel, and we'll see what we can build together.
Great. Awesome.
I do have a question.
Mm-hmm.
So you just said simulation problem. By the way, great talk. Thanks very much.
Thanks.
You just said simulation problems, and I do have some simulation problems at the moment.
Okay.
A way to simulate experimental data, in a sense, do you have some artificial noise models where you put, because at the moment my data don't look like the experimental data. And
yeah.
That at the moment.
Yeah, no, that makes sense. So actually the thing I was just talking about, so I think in general, the kind of task or problem you're looking at is open system simulation, or at least that's kind of what the community more broadly calls it. Currently in the QDK, there is not an open system simulator, but there are tons of open source open system simulators. And basically, it shouldn't be, I'm basically working with some community members right now to plumb those up so that we can do exactly what you're suggesting here, which is simulate experimental, you know, simulate whatever noise models or error models that you want, and then use that to actually run tomography sorts of protocols, or, you know, any of those sorts of good QCVV stuff. But yeah, that would be, I would love to learn more about specifically kind of like what noise models and sorts of things you're looking for, so that we can figure out, you know, what are the most useful simulators or open system simulators to hook up first.
Yeah. Okay, I'll get in contact with you. Yeah.
Awesome. Thanks.
Great.
Maybe I have one quick question too, which is
Sure.
Aside from the sort of stepping aside from the open source community thing, if you are wanting to set up as a PhD student, say, and you want to learn how to do like proper collaborative code development, like you want to set up a project so that you can have multiple people developing this, and you want to do that in a good way, you've got access to something like GitLab or whatever, and is there is there a single resource that you would say, right, go read this if you want to learn how you should do this, if you want to learn about all the things like unit testing and all that sort of stuff? Is there a place that you would recommend going for that?
I don't have necessarily like, this is the one resource. I did link to a couple in the talk that are good. I'm just trying to, I will grab the links to put them in chat here. One sec. But like actually GitHub maintains a pretty good like guide for, hey, you're starting a new project. You know, here are things you may want to consider. Here's, you know, here are all the setting options, at least for GitHub, GitLab, and all of those are going to have similar things like, you know, do you want to push protect master? Like what does Git even mean? So a lot of those resources, I think. Another thing I could mention is actually back when I was at Macquarie, Chris, Ferrie, I think you did it with us, Chris, but Chris Grenade, myself, and a few others actually did a 2-day workshop for Equus, where we went through basically all of the basic computer science skills that you would need as kind of like a researcher. You know, generally we were kind of gearing it towards early grad students, but perhaps like even postdocs and stuff I think could benefit from it. But basically we went through, you know, everything from basic, what is the command line, through using, in that case, we were focusing on Python. So using Python for instrument control, using Qtip, stuff like that. So I will put, let me link to that in the chat real quick. But yeah, that, and we've honestly been trying to figure out how to get maybe funding or support to update that. I think most of the content is still fine, just maybe the Python versions need to be bumped. Mm-hmm. So. But yeah, I think you've correctly identified a resource that, you know, as a single point of reference would be a really useful thing for research.
Right. Because I heard the term yesterday. I heard the term gradware, and as in something that people are like, especially the industry community in quantum is desperately trying to move away from. And I think as grad students coming into the field from the research side, we don't really get any training in this.
Yeah.
And it would be great to learn. You know, there are people like me who are starting up a research group, and mm-hmm. I didn't get any training in that in my undergrad and in my grad studies, and it's really only just I've picked up some semi-reasonable habits just by osmosis, but I also have a lot of bad habits, and I'd like to, you know, set things up better than that.
Yeah, and I think, you know, something that kind of, so I put the link to the workshop in chat, and the other links are in the talk on the slides, but I totally resonate with that. And kind of one of the things that in some ways drew me away from research was I really appreciated those processes and seeing how they actually made doing the work that I was interested in a lot easier and better. Like, I remember distinctly working at one point where our data, the raw data for our experiments, were on one jump drive that was a like intern who then we never got that jump drive back, and then we were trying to publish the paper and couldn't get that raw data back.
Yeah.
Like, we had the rendered plots and stuff like that, but we did not have the actual data.
Yeah,
which,
yeah.
you know, there's some issues there, right? So, you know, I think it's kind of, like I mentioned before, one of the things I'm most excited about at this point is, you know, I really like trying to find ways to connect researchers like myself with these resources that I now know at least exist, even if I don't know how to do them. Like, I know a lot about what DevOps can do. I can't necessarily do all of it, but I like to dabble. But I think like there's so much we can do to actually improve our research and actually do more research with these tools. So yeah, please feel free to ping me if you have any specific questions or anything. But yeah, I think, or if you want to collaborate on doing another iteration of that workshop, I think that'd be really fun.
All right, great. Thanks, Sarah.
Mm-hmm.
All right. Well, that was great. So thanks a lot for the talk, and yeah, we'll see you in the community.
Yeah. And have a great day. Thanks so much for having me. And remember, the Wicca community tagline is, remember, quantum isn't magic, but you are. So I will leave you all with that thought.
Thanks, Sarah.
Bye.